Suppose you have an object that's moving in three-dimensional space. And we want to know how far the object has gone or what force was necessary to move the object. Now, these are all questions that calculus can answer, but first we have to have a way to describe the path of an object as it moves through three dimensions. Now, we already have tools that let us do this in two dimensions. For example, the equation x squared plus y squared equals 1 describes the path of an object moving in a circle. Now, to move this up to three dimensions, the obvious thing to do would be just to add a third variable to make the equation x squared plus y squared plus z squared equals 1. Now, the problem is that when you add a variable, it takes us from a one-dimensional line to a two-dimensional surface, in this case the outer shell of the sphere, rather than a one-dimensional line moving or wrapping around in three dimensions. Now, the solution to this is what are called parametric equations. So to make things a little more straightforward while we're still getting used to the basic concepts, let's drop back down to two dimensions. What we have here is an example of a set of parametric equations. Now, when you hear parametric equations, what I want you to focus on is the parameter part. So what I've done here is, instead of defining one of the coordinates, usually the y, in terms of the other, usually the x, I've defined each of them in terms of a third variable called a parameter. Now, in theory, you can use any variable you want for the parameter, but t is the most common because in practical applications, it often represents a time element. Now, ultimately, we've got the same goal here as with the rectangular coordinates that you're used to describe a set of points in two dimensions, which we can connect into, in this case, a continuous curve. To do that, let's use the most basic approach and just calculate some points. So if t equals 0, then x of t equals 0, and y of t also equals 0. If t equals 1, then x of t is 1, and again, y of t equals 1. Now, for t equals 2, then x of t equals 2, but y of t equals 2 squared, which is 4. And finally, when t equals 3, x of t equals 3, and y of t equals 3 squared, or 9. Okay, so if we graph those points, then draw the smooth curve through them, you get the right-hand side of a parabolic curve. And if we repeated the process using negative values of t, we'd get the other side of the parabola. So looking back at the original equations, this makes sense. The x variable is increasing at a linear rate, and the y variable is increasing at a quadratic rate. Now, before we start thinking about points in the graph again, let's stop and think about what the functions are telling us. The y-coordinates are increasing at a quadratic rate, where the x-coordinate is increasing at a cubic rate. So we should expect the graph to be going out slightly faster than it's going up. So with that in mind, let's get some points and see where they take us. T equals 0 gives us 0 for both coordinates. T equals 1 gives us 1 for both coordinates. T equals 2 gives us 8 and 4. So we're seeing the x-coordinates start to pull out in front here. And finally, t equals 3 gives us 27 and 9. So to make this fit onto the graph, and I'm going to count 3 units for each grid line. And that gives us something that looks like this. Now, if we go back and redo the calculations using negative values for t, the y-coordinates are all going to stay the same, where the x-coordinates just have their sign change. So adding those to the graph gives us this shape. Now, the setup here is a little different from the previous two. Since the function definitions both use trigonometric functions, I switched from using a t to using theta, since that's a more natural choice for this kind. So to see what the graph looks like, I'm going to use the same approach and calculate some specific values. Substituting 0 for theta gives us 1 for the x-coordinate and 0 for the y. Pi over 6 gives us 0.866 and 1/2. Pi over 4 gives us 0.708. Pi over 3 makes the coordinates 0.5 and 0.866. And finally, pi gives us 0 and 1. Now, if I plot these points, letting 5 grid lines be 1 unit, so it's easier to see. And draw the smooth curve connecting them, we get a quarter circle. Which makes sense if you look at the original functions. We're looking at the set of points whose x-coordinate is the cosine of the angle, and whose y-coordinate is the sine of the angle. So if we continue plotting points for values up to 2 pi, we'll get a unit circle, which is what the sine and cosine functions are derived from. So now that we've seen how parametric equations are defined and looked at some basic examples, in the next lecture in the series we're going to look at some more examples and use them to illustrate some of the additional advantages that we get from our new tool.